Hey everyone, and welcome to this video on pipe flow. In our previous video, we introduced the Bernoulli equation and the idea of energy heads. Now we're going to expand on that in relation to pipes. So here we can see a simple pipe section full of water running from left to right. Now, without any specific calculation of quantities or distributions, we can see here the three heads: static, velocity, and pressure, and the total energy line made up by their sum. Now, if we were to write out our Bernoulli equation to compare either ends of this pipe section, we'll label them locations 1 and 2, the pipe is running horizontally, so the static head has no reason to change. There is also no change in diameter, so the velocity of the fluid inside, and hence the velocity head, has no reason to change. With that knowledge and applying our understanding of conservation of energy, the pressure head should remain constant, shouldn't it? So that the total energy of the fluid is kept constant. However, in our previous video, when we looked at our experimental apparatus to demonstrate the Bernoulli equation, we saw a loss in pressure, and the reality is that this will be the case again. This is because up until now, we've used an idealized form of the Bernoulli equation, which does not take into account a number of factors which cause head loss, one of which is friction, which we will discuss in this video. The reality is, fluid will lose some energy as it flows along this section of pipe due to the friction between the fluid and the pipe walls. So, a more realistic energy diagram would be this. We actually see a loss in head occurring due to friction, so we can label this loss HF. Now, it's important to note this head loss is taken out of the pressure head component. Our understanding of the velocity-area relationship from flow continuity still remains true, and thus the velocity head and static head are unaffected by this head loss. This term HF must simply be added on to the end of our Bernoulli equation to give this more realistic portrayal. It's also important to notice this head loss varies linearly along the pipe, simply letting us know that the longer the length of pipe the fluid travels along, the greater the head loss. This gives us our first important relationship, that frictional head loss caused by a pipe is proportional to length. Now, to demonstrate the other properties frictional head loss depends on, we've built a simple pipe rig. Water enters here, flows through a series of different pipe components before exiting out the other side. Similarly to the Bernoulli experiment from the last video, there are a series of tubes taking pressure readings at different locations, and then displaying them on this piezometer stand we can see here in the middle. This will allow us to see what components cause what kind of head loss in the fluid. So there are a total of 9 pressure readings, which will each show us the rate of head loss across different kinds of changes in the pipe. Let's start by taking a look at the first 3. All 3 of the first readings are located on the same piece of pipe of constant diameter. All 3 of the readings are located the same distance apart, and therefore experience basically the same head loss between each reading, as we now know head loss is proportional to length. However, we can now test another interesting relationship. By steadily decreasing the flow going into the pipe, and hence the velocity of the fluid inside, we can see what the relationship between the speed of the liquid and the head loss is. We recorded the data for 3 fluid velocities, and we can see here that the head loss is getting smaller with the decrease in velocity. And then, by simply plotting this data onto a graph, we get our second important relationship, that head loss is proportional to the square of the velocity of the fluid in the pipe. Importantly, the final section of the pipe rig was made out of a different, wider diameter pipe. The piezometer tubes are spaced the same distance apart as those opposite on the thinner section. Therefore, we can see how the difference in diameter affects the rate of head loss if we compare the first two readings with the last two readings. When we look at our first two, we see relatively large head losses occurring between the recordings. However, for the same distance apart, a drastically smaller loss during the larger 22 mm pipe diameter. And this shows us our third rule, that head loss is inversely proportional to diameter, meaning the larger the diameter, the less head loss that will occur. So with all that being said, let's review. The rate of head loss that occurs to the fluid in our pipe will be proportional to the length of pipe over which it travels, inversely proportional to the diameter of the pipe, proportional to the square of the velocity the fluid inside is traveling at. Now remember, this squared velocity term relates to kinetic or velocity head, so we can add our constant 2g without changing the fact that head losses are proportional to the square of the velocity, as we saw before. So putting this all together, we have this relationship. Now, the last step then relates to determining what the proportionality factor, which we call lambda, depends on. Well, empirical evidence shows that lambda is not a constant, but actually depends on the pipe material and the flow regime, and is determined by empirical means, as we shall be seeing in due time. For the time being, though, it's sufficient to say that we finally have an expression to estimate the head losses in a pipe, which is this. This is known as the Darcy Weisbach equation, and lambda is called the Darcy friction factor. Hopefully you now all understand the source of all these different variables which make up this really important equation in pipe flow. The one which is probably new to many of you and the hardest to understand is the friction factor lambda. This friction factor depends on the flow regime, such as whether the flow is laminar or turbulent, which you can see examples of in the background, but it also depends on pipe material. As this is a more complicated variable, it will be explained in more detail in the next video.